Thank you for the warm welcome. And also, I thank Adon, Dr. Adon, for inviting me to this particular talk. Um, Today, I'll be talking a little bit different from what you have been witnessing for for one day with different talks. So this is uh, atomic molecular optical science using attosecond pulses. So I work at the Raman Research Institute, as the introducer told. So the work which I'm talking today, mainly the work that I've carried out in different places. This is Australian Attosecond Science Facility located at the Griffith University and the UMIA University, where the relativistic attosecond facility hold, and then extreme light infrastructure beam lines. Also, at the Raman Research Institute. So if you have any questions in between, please post me and you could ask. So before directly entering to the topic, at Raman Research Institute, we have, this is a fundamental physics institute where we are dealing with four different areas of research. One of them is light and matter physics, and the second is astronomy and astrophysics, and third is theoretical physics, and the fourth one is soft and condensed matter. If you are interested, just go to the website and see what kind of research are going on inside this laboratories. So in this particular talk, I'll motivate you a little bit on why do we need short pulses like attosecond pulses, and how do we go forward for the generation of such pulses via, and mostly it is via high harmonic generation. And then once you have high harmonic generated signals, how do we make it attosecond pulse? And then I'll talk a little bit about attosecond nonlinearity, not too much, and then different applications of attosecond pulses that you can actually do in the future. So you can see two different videos, one on the left side, one on the right bottom. So here you could see some difference. One could argue that on the left side the traffic is slow, or the vehicle are moving really slow, and on the right side it's a freeway, and therefore vehicle are speeding faster. For us, like physicists or scientists, the difference between these two are the technological limitation of the camera. So the first one, we have a very good camera to capture information, and the second one on the right side, if we had a very good camera, like a faster camera, we could actually get the information of the speeding vehicle rather than the light or a streak of light which is flying. So the question now arises, okay, can we make such cameras? Okay, good for the roads. But what physicists think, we need to advance technologically, and there are cameras available nowadays, and you could actually count and take frames and images. Now, what ignited us in this case is that, okay, one of them is very fast and the other event is slow. So if you want to capture fast information, you need to have a better camera. This is what the takeaway message from this motivation. Now, what is actually, that to do with physics or the science? If you are all familiar with, I understand you are all familiar with Bohr atom model, where it's a classical model where you can consider the atom has a center, which is nucleus, and here it is represented by green ball, and the electron is surrounding the Bohr, surrounding in the Bohr orbital. And let's say this is n is equal to 1 orbital for a hydrogen atom. I think you can also see my mouse, or can you?
Yes, sir.
Yeah, you can see my mouse, the pointer, right?
Yes, sir.
Okay, cool. So the electron, the white electron represented by this white ball is revolving around the nucleus. Now, if you know the radius of the first orbital, you would be able to calculate what is the length at which it takes for one revolution. So the distance it travels from here to all the way and comes back to this point. And this is the distance it travels, and the time and in which it travels is also can be understood. So from this data, one can calculate what is the time at which the electron revolves around the first orbital of hydrogen or even second orbital. So you can calculate mathematically. This is available. But this is so classical, and we know that the system doesn't do that way, and it will be more like the reality of represented by quantum mechanics, and it is on your right side. So this is black, and then the probability density is what it is. So it's like you have the center nucleus, and then things are moving. So you can see that the things are actually or the probability of electron you can see like this or visualize like this. Now, go back to this again. Go back to the old classical model, which is not valid for a particle like electron. But then, for a simple approach, we can actually take this as classical and to calculate Bohr orbit time. And when you calculate Bohr orbit time, what do you see that? See, this is the expression which you can actually find in any of the textbooks. So when you calculate that, you get 152 a second. A, it represents atom. So it gives you 152 attosecond for one revolution. Now the question comes into physics. Oh, okay. If I have 152 attosecond, can I see the motion of electron around the nucleus? Or maybe not, because we need a faster system than the event to measure it. So let's say if I have 50 attosecond, for example, I could capture 3 times before it reaches one revolution, reaches back to the original point. So if I make 50 attosecond, I can capture information and then go on doing this experiment multiple times will lead to a complete picture. Now, as I said, this isn't true. This is not true. Quantum mechanically, if you look at the system and you write the ground state wave function or the eigenstate, then the equation represents like this, and it has an exponential term which has a time factor in here and a wave and a space function. So it's a multiplier of space and time. Now, when you really want to look at the number of electrons or the probability of finding electron, you just make the mode square of the wave function. If you take that, you find out that there is no temporal term in the probability electron distribution. There is no temporal term. There is no time. So the t is not involved. Only r is involved. R is a space variable. When it is space, then there is no denox. Now the question is that with one orbital, you can't have any dynamics, and therefore, what you need is to have coherent superposition of two wave packets, the two states, which is a wave packet. Simply, it means that if there is a transition between one level to the other level, so if there is a transition between these two levels, then those two states, I mean, the transition or the superposition can be represented by the combination of these two levels. And then take the probability density of electron. So when you do that, you get a temporal, there are terms, but I'm not interested in the first two terms because there is no t function, the time function. Whereas in the last term, you can see a time factor. With respect to time factor, you could calculate what is the oscillation period between those states where the electron is transiting or moving. So, or vice versa. And then with that, you can calculate the oscillation period. So when you calculate the oscillation period, it boils down to the difference between the energy levels. So it is inversely proportional to the difference between energy levels. Now, the problem is that we need to look at what is the separation between the energy levels that you are interested in. Now, let's take hydrogen atom. And we know that it has 1s orbitals and 2s orbitals, forgetting all the quantum mechanics and the parity, because parity violates some of the things that I'm going to explain. But forget all the parity and quantum mechanics. Let's say that you have 1s level and 2s level, and you try to understand, you can hypothesize that there is a transition between 1s and 2s. And if there is a transition between 1s and 2s, and you know the energy difference, because hydrogen first orbital is 13.6 eV, and the second orbital you can calculate. So when you calculate, you have 13.6 eV as the first orbital and 3.4 eV as the second 2s orbital. And the difference is around 10 eV. Plug the 10 eV here, energy, in this equation. You get a time period. And which is what you see here on the left side of your slide. So what you see here is the height of the peak. The highest one is 1s probability density distribution. This is 1s probability density distribution. Whereas this one, the ring on the side, is the 2s probability distribution. So the 1s electron is actually moving to the 2s electron and vice versa. This is called breathing oscillation. And this happens for a time period of t given by h by 10 eV. And this comes around 420 eV. Oh, sorry, 420 attosecond. Now we have more than interesting things that we could actually do with attosecond pulses if you can generate them. So the idea is that okay, you have femtosecond pulse and other pulses, but do we really need to go to attosecond? Or what physics can be understood if we can generate attosecond pulses? Now the answer is clear. There are so many interesting physics that you could actually look into. Depending on the delta E, you could see that what is the time scale. Now we'll go for a broad class. The broad class is, yeah, let's talk about stopwatch. Stopwatch can give you 1 second resolution, whereas the fastest camera can give you 10 to the power minus 3 seconds resolution, which you can buy in the market, and then you can look at. I mean, you can record the videos and what else you can do. You can record the flying objects, etc. But if you really want to look at chemical reaction, you need to have at least 10 power minus 6 seconds, which is called a microsecond, and you need that kind of a resolution in the detector to measure chemical reaction in a temporal manner. So now, if you go to fast electronics, like the chips in your electronic devices, the electrons are moving there. To look at those electrons, fast electrons moving in chips, you need to have at least an nanosecond resolution. Now, if you go to a rotation, see, let's say you're looking at rotations, and let's say if you want to look at vibration, molecular rotation and vibration, which falls between picoseconds to femtosecond timescales. Of course, now you say, okay, photosynthesis, what is photosynthesis? I mean, you know photosynthesis, everyone knows photosynthesis. It happens around 10 to the power minus 12 to 10 to the power minus 15. But we are interested in more intrinsic phenomena. What happens to electron motion? And what is the timescales of electron motion in atoms and molecules? And when you look at that, I mean, we are talking about an EV or some sort of differences. When you plug that number in the time equation, as mentioned in the box, the box here, you can see that it is of the order of femtoseconds to attosecond. Now, we need attosecond pulse to understand those motion, which is really fast. So the motivation is the real-time observation and direct control of electronic motion in atoms and molecules and nanostructures. To do that, you need a shorter pulses or a fastest camera. So here comes the camera, because you are trying to understand a speed process, a process which is occurring really faster. And there, you need a camera, and that camera is the fastest camera available in the world, and it's called attosecond pulse. It's not a direct camera, but an indirect camera which could capture or that could capture information in those timescales. Now you understood, so you can actually look at the electron motion in your material you develop. You develop a material and you want to know what exact physics is happening in the system without actually considering the macroscopic nature. You need to know what you need to pinpoint when you do something, what is the modification happening in the system. If you want to do that, you need a shorter pulse. Now, what is attosecond? Compare the time scales. When we compare the time scales, attosecond is something like you write a 0 and then 0 point, then 17 zeros, and then the last one. So it is called the billionth of a second, which is 10 power minus 18 second. It's incredibly short time. When you compare that attosecond time scales to 1 second, the blink of your eye, then it is it is equivalent to comparing 1 second to the age of the universe in seconds. Now you see how incredibly short the time scale is. So generating such pulses was challenging before at least 2000. Sorry. Now, what we have had before 2000, we had already femtosecond pulses, which is 10 to the power minus 50. These pulses were available. Even in soon after the discovery of laser, these pulses came as a byproduct of Mott blocking, which you can actually look into any of the textbook, which is out of the scope of this particular talk. But then when you have a femtosecond pulse, and you look at what is the wavelength inside the femtosecond pulse or the carrier frequency. So you need to have light, right? I mean, the light has a color. And the color generally is around 750 in most of the tabletop femtosecond laser system available in the laboratory in those days. So suppose if the femtosecond light is emitting at 750 nanometer, and when say 700, when somebody says 750 nanometer, it is the distance between trough to trough or crest to crest, right? It is the difference between the crest to crest and the trough to trough. Now you look at what is the time scale for that much length. 750 nanometer is a length, and let's say light is moving and then through that distance, and what is the time scale associated with it? You can calculate by distance by velocity would give you time. Here the velocity is c, velocity of light. And if you divide 750 nanometer divided by the velocity of light, you would come back to time called 2.5 femtosecond as mentioned here. So basically from here to there, one has to travel with the velocity of light. It takes 2.5 femtosecond. What it means that with 750 nanometer, experimentally, the minimum that you can generate, minimum pulse duration that you can generate is 2.5 femtosecond. Now we were talking about attoseconds, which is far down to femtosecond. It is impossible with 750 nanometer. It is really impossible with 750 nanometer. So how do we proceed further? Now, we do the same exercise for 30 nanometer. So take 30 nanometer, and the crest to crest or the trough to trough distance is 30 nanometer, and divide it with the velocity of light, gives 0.1 femtosecond. 0.1 femtosecond is 100 attoseconds. So you have 100 attosecond with you now. Got the idea? Now, to generate attosecond pulses, the problem now boils down to generating 30 nanometer or somewhere close to the 30 nanometer or somewhere around 30 nanometer. If you really want to look into 100 attosecond, you need to generate them. But what you have in the laboratory those days is 750 nanometer, something like 5 femtosecond. And how do we generate them? So the problem in those days to generate 30 nanometer or somewhere close to 30 or 50 nanometer, depending on what the pulse duration you need. So ultimately, to observe the electronic motion in atoms and molecules, you need to generate something called really short wavelengths. These are called extreme ultraviolet or XUVs. So generate XUV from visible or IR is the problem. So those days, what people had was an oscillator, a femtosecond oscillator, typically gives 5 nanojoules of energy, around 800 or 750 nanometers, I said just now. It could generate 6 to 7 femtosecond using some phenomenon. And then, because the energy is very low, what people actually crank up the energy by amplifying them. It's called CPA, chirp pulse amplification. What they do is the following, and this is out of scope of this particular talk, but this is available in the laboratory, and this particular method is called chirp pulse amplification and received Nobel Prize. And this particular technique received Nobel Prize in the year 2018. And with respect to this particular technique, 5 nanojoules can be amplified to something like 5 millijoules. So you get a 10 power 6 gain. Nanojoule to millijoule is 10 power 6, 10 to the power 6. So that kind of a gain is possible. And with respect to that, you have an amplified femtosecond pulse, which could be utilized for different process. In those days, people had this, or the scientists had this. What they did was they just focused this light. This is your 5, let's say 5 millijoule. 1 millijoule is more than sufficient, or less than that is more than sufficient for this experiment. However, so assume that you have femtosecond pulse, you focus it onto gas jet, which people started with noble gases because they don't want to have any other phenomena in between the atoms. So they focus the light, the femtosecond light onto the gas, and just looked at what happens after it by a spectrometer. But the spectrometer here is the range, has a range of 20 EV to 100 EV. When I say in 100 EV, you should also understand that roughly 800 is 1.5 EV. So 150 EV is 100 of 800 because 800 divided 800 is 1.5 EV. So 100 of 800 gives you 1.5 multiplied by 100 EV. That means 150 EV. So 150 EV is 100, 800 clubbed together. Okay, so what you see here is a spectrometer looking at 20 EV to 100 EV. I think that you understood the concept. So then annular so that, okay, there are certain radiations coming from 20 EV to 100 EV. But when they tried to model it, they could not get any information out of it. I mean, they could see that this is a nonlinear process. It's not a linear process, nonlinear process. And then there is frequency range in which the intensity of the emitted radiation are constant, and then there is a cutoff. So you get series of frequencies, and these are called harmonics. So what they got is harmonics. So 800, the second harmonic of 800 is 800 divided by 2, which is 400. Then the third harmonic of 800 is 800 divided by 3. Similarly, 800 is 1.5 EV. The first harmonic of 800 is 1.5 itself, and the second harmonic is 1.5 EV multiplied by 2, which is 3 EV. And similarly, and so on and so forth, you get multiple harmonics, and those are the harmonics represented by these colors. So the yellow here represents the nonlinearity, which is lower nonlinearity. And then the Plato, they could not explain, represented by red here, and the blue cutoff, they could not explain. So this was the first paper on high harmonic generation. Now the problem is that they could not explain much of the things that they detected. One is Plato and energy cutoff. And after doing this, the process is something like 10 power minus 6 or minus 7 efficient. That means if you throw in millijoules of energy, finally what you get is nanojoule or a picojoule, hundreds of picojoules of energy, which is insufficient for most of the process that you're looking at. And therefore, how to improve the efficiency so that you get more energy from the system. That's second thing. The third thing was, what is the duration of such pulse, whether it is attosecond or a femtosecond. So because we were trying to generate attosecond, but then we don't know what it is. And what are the applications? Do we need to advance technologically? Because after doing all this, we even though we advance in technology, if we don't have applications to proceed with, there is no point in actually doing it. So these questions they asked themselves, answered many. So this is one of the pioneers in attosecond science, and he received Nobel Prize in the year 2022. This is the Professor Paul P. Corkum, and he gave an insight to the process. And he said that, okay, fine, what you do is you have atom, you have atom, and you come with an electric field. When you come with an electric field to an atom has a Coulombic potential. Similarly, the electric field has its own potential. So if the intensity is so high that the Coulombic potential, now the modified Coulombic potential is the superposition of the potential of the electric field and the Coulombic potential. So what it does is the Coulombic potential of the atom or the electron is sitting in the Coulombic potential of the nucleus, and which is getting modified. When it modifies, at some point, there is a chance called some part of your wave function is going to get tunneled. And the tunneled electron would come out of the system represented by one called strong field ionization. With the strong field, part of the wave function can come out. And then upon coming out, it comes out with zero kinetic energy. The electron, if you consider it as electron, it comes out with zero kinetic energy. But now, this happens in a fraction of time, like in of the order of instant. You could call 6 attoseconds or so, or less than that instantaneous process. It is a debating problem at the moment. So the best people have done is 6 attosecond. So let's say in 6 attosecond it comes out, which we don't know exactly, but then it comes out, and then it immediately see the long laser field, and the electron that comes out actually forced by the field. It goes out of the system and then comes back upon reversing the electric field. Because it is oscillatory electric field, it goes up and down. When it reverses the direction, the electron that goes out of the system comes back and interact with the parent ion where it started with. So these three processes, like strong field ionization, take the electron out of the system. The propagation is called the electron is actually accelerated within the electric field of the driving field. And the third portion is called recombination. It puts back to the system. So when it puts back to the system, when the electron is put back to the system, what happens is that the energy that it acquired, the electron acquired during this process, has to emit. So this emission leads to harmonic generation. And this is what his explanation, and is like more like a layman model, but he did quantum mechanical theory along with Anna Euler to establish it. Now, this is the video. Maybe there is a sound, but then I can. Sorry, there's a sound. Bear with that sound. The timing. This is the process what I say. So you have electron, and the electric field comes in. Electric field is red, and the electron goes out, and it follows the trajectory of the field, and then it comes back. When it comes back, it produces photons, which is of XUV energy because of the energy that it actually acquired during the process. Now there are many such atoms, and all these atoms are going to contribute to this electric the generation. And if they are phase matched, you will get a decent amount of harmonic. If they are not phase matched, it destructively interfere and you won't get harmonics. And this is a process. So what you essentially do is you focus femtosecond laser onto the gas, producing XUV, and look at the XUV. Now this experiment, and theoretically it can be explained. Let's say the electron is emitted at the peak of the pulse, and this is the time scale. So x-axis is time, and the y-axis is distance from the ion. So the ion is sitting at 0. So let's say the ionization happens at the peak of the pulse here. The dotted black represent the electric field, which is represented by this equation: E of t is equal to 0 cos omega t omega 0 t u of x. And then the electron. The electron comes out at this point, let's say ionized at this point. Now we need to find out what is the velocity and what is the trajectory of this electron. You can actually use this equation to calculate the velocity by using dv by dt. So you change this to this format, because this is a force. Force is F is equal to Q into E. So E is the force, and dv by dt is minus E by m into E of t. And then with respect to this, if you integrate with boundary condition, you get velocity, and you integrate again with boundary condition, you get x of t. So you have position and velocity. With respect to position and velocity, you can also find out the time at which the electron comes back to the system. In some cases, the electron doesn't come back to the parent ion. In some cases, it comes back with 0 kinetic energy. In some cases, it comes back with the different kinetic energy. So you can find out the time scale. You can find out explicitly everything with respect to that equation. This is simply a classical equation. Now, he has also mentioned in his one of his paper, and it is widely accepted as the cutoff energy that we mentioned. The last energy that you get in your HHG is ionization potential plus 3.17 UP. UP is quantum energy. Forget that. This is a contribution of lambda and intensity of the laser. So this is what you get. So you get some cutoff, and which is given by here, given this point at this point. So now we'll look a little more deep into it and then see. So you have electron, which is generated over here, and the electron goes all the way. This is the distance from your parent ion. Y-axis is your distance. It is taking away from your parent ion. It puts back to the system at this point. When it comes back to this point, and when we calculate the energy, it comes out with 0 kinetic energy, leading to no harmonics. Now let's say the electron comes out, or electron ionizes. around before the peak of the pulse. Now, the black line is where your ion is, whereas the electron is not at all reaching the ion. Therefore, it doesn't reabsorb by the ion. And it is also not going to give high harmonics. And if you look at the third case where the electron is ionized at this point, you can see that it comes out with some energy around this point. So this is where your parent ion and like chances of generating harmonic. Now, if you take a series of such process, you can see that because it is ionized at different point, it will take different paths, different ionization time, leading to different energy of the photons that you are, electrons that you are coming back to the system, and therefore it leads to different energies. So here you can see that because it takes a shorter route, it comes with a lower energy. And likewise, you go different trajectories, you can get different kinetic energies, and hence you get different photon energies upon recombination. And you can model this process either quantum mechanically or classically, depending on what you like. So now the thing is that now you have harmonics, and if you have harmonics, if you can do some technical advancement, you would be able to make it as attosecond pulse train. So what you started with a femtosecond oscillator, and then you amplify and use that to focus on to gas cell producing harmonics. Do some sort of modification on your pulse or something on the way to the pulse. You could either generate one XUV pulse or many XUV pulses. If you can generate one of them, this is called an isolated attosecond pulse. That was a challenge in the initial days. However, the series of attosecond pulses is straightforward. So what you essentially have is like the first observation was harmonic spectrum, which you get many different frequencies, which are called comp frequencies, comp frequencies, and the comp frequencies can be easily generated. And if you could select a particular attosecond pulse, which is not that easy, you could get a broadband spectrum, and which is useful for many different application. And the other thing, attosecond pulse train is also has applications in different fields. However, so in one stretch, if you have all this, if you select one of them, you can generate attosecond pulse, isolated attosecond pulses. If you have this, you have broadband harmonic spectrum. And if you select one of the harmonic spectrum, you get femtosecond XUV pulse. And if you select that one, if you have, and then you can have frequency comp. If you narrow down to one of the frequency comp, you get narrowband CW laser, XUV laser. So the problem is now it's like a bunch of thing that you get. So you started to generate attosecond pulses, but then if you can advance technologically a bit more, you can get a continuous laser like the normal helium neon laser that you have in the laboratory, and then you have femtosecond XUV laser, and then you have attosecond pulse. This is so rich, and if you select this or tune this, you can do multiple experiments related to electron dynamics, probing and controlling matter, development of advanced technologies and applications in applied sciences. So this is a rich field. Now, so we were actually working on the development of isolated attosecond pulses from this broad system, and we could actually get attosecond pulses of about 150 attosecond, modifying the fundamental oscillator amplifier geometry, and that to a long talk and a discussion for like a, I would say if you really want to know, it will be like a 15 hours talk. So therefore, I'll keep it aside. So now I would like to explain how to generate that. In a video, I'll play the video and then post a bit from talking, and then you will see what it is. So I explained everything, but then yeah, you can go forward. So now the electron wave function goes out of the system at one time, and then comes back. I interact with the rest of the wave function, which is really, and then when it interacts, you generate harmonics. And this is the process. incredibly smartly explained in the video. So when the electric field comes, because the electron is sitting in the Coulombic potential, if the electron has to go out of this system, it should do some sort of tunneling, at least for this process, for the harmonics. So you can see the tunneling happens because the potential bends, and then upon reversal of the electric field, it comes back and do the interference. It's called interference because it's a wave function. A part of the wave function is already there, and you go out with another wave. I mean, the part of the wave function. The wave function that goes out comes back, interfered with the original wave function sitting over there, producing harmonics. And this is what your isolated at a second passes. Now, what you can do with this? Now, this is one of the laboratories where I visited, and we have some collaborations. And I'm fortunate to have collaborations with Anna Lulier, the 2023 Nobel laureate in attosecond physics, and I've been working on one of the instrument to detect these electrons, and they had an instrument. I copied their instrument and modified the instrument for our kind of experimental setup in Sweden. And this is her laboratory when I visited, and it's still intact. And there they have a tangential laser system for different. I mean, they generate attosecond pulses and do this attosecond pulses for different processes such as multi-photon process, charge migration, coherent imaging is what they do in their laboratory. And you might be familiar with this name because she received Nobel Prize in 2023. Now there is another lab which I could not go because this is another professor who shared this Nobel Prize with with Anna Lulier, Pierre Agostini, and this is his laboratory where he is conducting attosecond pulse measurement using the old technology that he had in mind. He had done with electronics. So this is a rapid, and where you could actually generate attosecond pulse strains and measure the duration of the pulses. And then the third one is Ferenc Kruse. I'm fortunate to work with his deputy director, Professor Laszlo Weiss, and that is the brightest attosecond beamline available in the world currently, and I work with them. So this is one of his many laboratories in Germany, where they could actually generate isolated attosecond pulses, and he's the person. He's considered to be the father of attosecond, and he also received Nobel Prize in the year 2023, together with Pierre Agostini, Anna Lulier. Yeah. Now, what they do is actually the application is the following. So if you have a molecule or an atom, you come with an attosecond pulse. So the violet is your attosecond pulse here, or the XUV pulse. And then the red is your fundamental driving pulse, which is a femtosecond pulse. You generate some sort of ionization inside this medium, and then look at the ionization as a function of delay between the XUV and the IR. So you change the delay between XUV and IR and look at the photoionizations. With respect to this, you would see how the electron is actually, moving after or moving within the atom or during the process. So if you look at those processes, you could actually have a sort of understanding of electrodynamics in materials. So this is what generally the experiment is, and this experiment basically mentions the pulse duration characterization, and a similar experiment would reveal how effective you can use these pulses for different application. Now, the application of attosecond physics is attosecond experiment is electron ion spectroscopy. So you can pinpoint from which ion the electron is coming from, and you can understand the intermediate processes inside the atom. So then you can also do high harmonic spectroscopy, where you can easily look at the rotation and vibration of the molecules affecting the harmonics. So when you have an effect in the harmonic spectrum, you could actually pinpoint what actually happens in your system in of the order of femtosecond timescales. This is really important to look at what happens, and you can see how the stretching and bending happens in the system upon vibration. You can see that stretching and bending corresponding to the emission intensity difference due to phase changes. So this can be modified, and I mean this can be well understood by attosecond science. Without attosecond process, it is impossible. Harmonic spectroscopy, it is impossible. Now, attosecond nonlinearity. What nonlinearity you have studied in your classes is basically the nonlinearity, two photon absorption, two photon processes. But what we look at is two photon ionization. Can we do two photon ionization? It's like you send in a photon and then extract. Let's say if you have 100 EV photon and you get 200 EV electron out of the system, that means 200 EV photons are getting absorbed to ionize the system. Such studies can be done. We have done sort of experiments back in field. Then, of course, you can do UV pump probe spectroscopy for the dynamics, UV IR pump probe spectroscopy for the dynamics of different species that you are looking at. Now, this is the timescales of their experiment. You can see in 2002, then the time resolved atomic inertial spectroscopy received Nobel Prize, but not period destiny. That was hello, can you hear me? Hi, hi Anshu. Hi, is there anyone? Okay, all right. Okay, so yeah, I'll continue. Just continue. So in 2023, they received Nobel Prize. Now, what's my role here is one of the okay. So what my role here? So I am fortunate to work with different guys like DJ Weiner, who is a Nobel laureate in 2012, and the first author of that paper is Professor for the paper that at which in which he got the Nobel Prize is Professor David Kilpinski. He was a PhD student there at that time. And then I'm fortunate to work with Professor David Kilpinski and a student of Paul B. Corkum, who actually defined or theoretically how high harmonic is generated. I'm fortunate to work with Professor I.B. Letinwick, Rika B. Letinwick, who was his student. And then what I did was in Australian Tuscan Science Facility, I built this facility along with one PhD student and two postdocs. I'm sorry, along with the one PhD student, two master student. This facility could actually look at harmonics around 70 eV. And now in Sweden, I'm fortunate to work with Professor Lars where we could generate setup where we can do XUV pump probe experiments at 150 eV. And there, to look at those processes, I had to collaborate to Per Johnson, who is a subordinate of Anna Lulio, Nobel laureate, to um, to construct this velocity by basic spectrometer, one of the detectors, which is not readily available in the market. We had to construct. I constructed this, simulated and constructed this for their mission. And there's another place where I worked, and here you can see how long is the line for the experiment, just to get a get a picture. And with this, what we are trying to develop here and in RRI, which is under construction, is a laboratory for attosecond science, hoping that we would come up with real picture in 3 to 4 years of time. So with this, I would like to stop. So what we can do is, as you see here on the right side of the image, so you can look at things in attosecond time scale to understand it better and redefine some of the things that are not readily available. So because you could not actually look at the fundamental process, though quantum mechanics explains many of the process, physically it was impossible due to time constraints. And now you have a tool which could actually look at those processes. If there is something to be readdressed, we could actually readdress. Thank you.
Now it's the time for a discussion. Those who have any doubts or questions can proceed right away.
Can I? Mhm. Can I stop
Hello,
sharing
sir.
that? Hi. Yeah.
Hi, sir. Actually, my doubt is now we are at the limit of attosecond. You all are working on that, right?
Yeah.
So, what is the ultimate limit, theoretical limit you can reach at for the pulse duration, actually?
It's already at the brim, I would say. So pushing further won't be that easy. Theoretically, you can go to any pulse duration. Hypothetically, you can do that. But experimentally, it's already challenging. So, in 69, if I remember, 69 or 70, we had the first femtosecond pulse, and it took something like um, 20 years from then on to develop attosecond pulse and to measure. See, the measurement was the problem. 89, we had the harmonics, and in 2001, where we could actually measure pulse duration. Now, technologically, there are a lot of challenges and it add to the cost. The problem with such a system is that you need to fund a lot, and gaining that amount of fund to build a system um, is not that easy, and therefore technologically it will be difficult. Of course, there could be someone at some point of time will come with a decent interest to build such system. But then we could actually measure indirectly septosecond. You got me, right? Hello.
Yes, sir.
Yeah, so 10 power minus 21, we had a resolution. We could actually get a resolution of 200 zeptosecond, which is 10 to the power minus 21. But that's not a direct measurement, it's an indirect phase measurement.
Okay, sir. Then next question is actually it may be sounds silly to you, but still,
That's
see
fine.
in our concept, we have an electron as a picture of both uh, matter and so with are we really able to take the photograph of an electron in that sense?
Yeah, I understood your question. So it's I mean part of them I understood because it's there was a glitch in between, like your sound was breaking. But I'll repeat the question. If that is not, just let me know. So can we really image an electron? This is what your question. It sounds like
Exactly,
that's it. Yeah.
exactly.
So it is not. It is impossible because quantum mechanics doesn't allow you this. So what you do is, you can't actually, take the photograph of the electron. Instead of taking the photograph, what you predict is the probability of finding them, right? So that you could predict. Yeah, since we have devices. I mean, now we have devices. Currently, we have devices. Even we can touch the one as electron. But that's not a direct photograph. But then, for your sake of understanding, the atom image, the image of an atom has already been done. Have you seen this? It's not an image, I would say, a shadow of an atom. Yeah.
Yes.
Have you seen this? I mean, yeah, I'm fortunate to work with D. Kilpinski, David Kilpinski, and he is the one actually recorded the shadow of the atom for the first time.
Okay.
So if you could actually go through his, I mean, you can see. I mean, he took a photograph, and it is a real photograph of an atom. That is done, but for the electron, I doubt. We need to come up with some sort of exotic idea, which is difficult. I cannot say because it's like, I mean, 20 years or 50, 40 years before, we didn't have a thought of generating a second pulse, right? So someone would come up with exotic idea saying that, okay, whatever you say currently is the limit of your theory, and the theory has to be readjusted. This is possible, but then the whole point today is that, I mean, we can go up to certain limit of septosecond to understand the system with a resolution, and we could image or at least to predict the probability distribution. Of course, yes, this is possible. Yes.
Okay, sir. Thank you, sir.
I do not know. I kind of locked myself, not actually. Okay, I just need to. Can I stop this screen sharing? Hello?
Yes, sir.
Yeah.